I have negative 3 plus 5, that is 2. So x is equal to 7, 2. It's the vector 7, 2, or I can think of it as the point 7, 2. Right? If I think of x as a position vector, pointing to the point 7, 2 in space. Right? So here I have, now this is why it's important that we always make sure that we differentiate between a point and its coordinates, right? Because 7, 2 might be the point, right? What we think about in terms of what the point is or what the vector is. And these are two different ways of being able to talk about how to get to that point or how to get to that vector, right? So that's why we want to be able to separate the difference between a point and its coordinates, or a location and its coordinates. Let's look at C. Find the coordinates of y relative to C. We know the coordinates of y relative to B is 1, 1. So that means, in this case, we need to use the, I want to go from B to C, so I want to use the second one that I have here. So I have y. I want to find y relative to C is equal to, and I have, in this case, I have B to C times coordinates of y relative to B. Okay, so BBCC. So what does it spit out when we do this? I'll put it down here. I have 2/3, 1, negative 1/3, negative 1, times y relative to B, 1, 1. Oh, you guys are like, Dr. Wesley, you did that wrong. Because it should be this, right? Oh my goodness. Yes, 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 yes. Yes, yes. You know, if you guys were here, you would tell me all these things. I make so many more mistakes. At least a mistake seems every video now, right? Because you guys are not here to stop me from making those silly mistakes. And I don't want to go back and redo all those videos again just to change one mistake. So a lot of times I just have to tell you guys to do email or something or on the video description. All right, so we have 3, 3, negative 1, negative 2. So what do we get here? 6, I believe is the top. And then this is going to be negative 3. So those are the coordinates of y with respect to C. What is y? Let's just do one of them this time. What is the vector y? Which one should we pick? I like to pick the one that's the easiest, right? Which one is the easiest to kind of translate over and to use in this case? And I think the easiest one of the two coordinates to use is the one from of y with respect to b, right? Just 1, 1. So I'm going to use that one. So what is y, the vector y? Okay, what is the vector y? Let's just use the, oh, I just erased my coordinates. What was it? Where were b? B was 1, 2, and negative 1, 1. Okay, so y is going to be equal to 1 times 1, 2 plus 1 times negative 1, 1. Okay, so if we add those together, what do we get? I have 0, 3. So that's my vector y. My vector y is 0, 3. And we can, if we can double check to make sure that's the case by looking at the coordinates of y with respect to C, and then using those to be able to figure out what y is. Okay, and go from there. So very, very, very cool. Now let's talk about the shortcut to finding the transition matrix. Now it's important to understand why it works, right? Because we don't want to think that it's magic or anything like that. There's no magic here. But there is a way that's a little bit faster to be able to find the transition matrix. And that's what we want to look at. How do we find the transition matrix quickly? When we're dealing with Euclidean space, so R2, R3, R4, R5, R1 million, okay? So shortcut, I'm just checking to make sure that the battery is still going on as we're still recording. Shortcut to finding the transition matrix. In Rn, I've had the battery stop in the middle, and I went on for another 20 minutes when I realized it wasn't recording anything. That's always a bad thing. Like, I gotta go back over that same 20 minutes all over again. All right, so here it is. Let B equal the vectors U1, U2 through UN, right? Because we're in Rn. Okay, so we need n linearly independent vectors. And C equal the vectors B1, B2 through Bn. B, basis sets in Rn. Okay, so both of these guys are basis sets that we're dealing with here. And so we can say the transition matrix from B to C, or C to B, doesn't really matter. From B to C, or C to B, can be found by using Gauss-Jordan elimination on the augmented matrix. C dot 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 B to obtain what we have here, which is going to be the identity matrix with the transition matrix from B to C in the right hand corner. And I'll get out of the way. Right, so the transition matrix from B to C can be found by using Gauss-Jordan elimination on the augmented matrix from C dot 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 B. So C here is going to be, we're going to have the vectors of C, right, are going to be as columns on the left hand side, and the vectors of B are going to be columns on the right hand side. When we do reduced row echelon form or Gauss-Jordan elimination, right, we're going to end up with the identity and on the left side, and the transition matrix from B to C on the right side. And the nice thing about it is you see that also in the way that it's written. So this goes from B to C, B to C, B to C, right? That's another reason why we want to have the arrow going the other way, right? So that when we do this shortcut, it still makes sense. This is going from B to C is right there. All right. Let's look at an example. Here we have, find the transition matrix. Find the transition matrix P from B to C, if C is equal to 5, 8, 1, 1, and B is equal to 0, 1, 2, 3. Okay, so these are C and B are basis sets in R2. I want to find the transition matrix from B to C. Now, what we could do exactly what we got to doing before, right? We could do exactly what we did before with the steps for finding the transition matrix. So what we have done in the past still works for this. But suppose we want to use a shortcut, right? We want to be able to use a shortcut. So what we would do is I could create an augmented matrix. Okay. And I want to go from B to C, right? So that means C is going to be in the left, on the left side. Dot, dot, dot. And B is going to be on the right side. C and B. Okay. If you do reduced row echelon form, this, you get this, and this is also in your notes. You get 1, 0, 0, 1, dot, 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 1/3, 1/3, -5/3, 1/3. Do not give me this as an answer, right? I'm not happy if you just give me this as an answer. I want the actual, this is an augmented matrix. This is not the transition matrix. This is an augmented matrix. So the transition matrix is going to be a 2x2 B to C that has 1/3, 1/3, -5/3, and 1/3. This is the answer I'm looking for. Okay. Do not give me this as the final answer, right? Of course, in WebAssembly you won't be able to do that anyway, but just in general, this is not the transition matrix. This is an augmented matrix. This is not the transition matrix. This guy is the transition matrix from B to C. And if I want to find a transition matrix from C to B, only thing I have to do is find the inverse of that matrix. One more, and I think we'll call it good. And this is actually the one I have first in the notes. It says this: find the transition matrix P from B to C, from C to B, from C to B. C to B. Or if C is equal to, I have 1, 2, 4, -1, 2, 0, 2, 4, 0. And B is equal to, what do I have here? Where is it? Oh, there it is. 0, 2, 1. -2, 1, 0. And then I have 1, 1, 1. Right, so notice that this is not in R2 anymore, this is in R3, right? But luckily for us, we have 3 linearly independent vectors for both C and B. These are basis vectors, right? These are basis vectors, and these C and B are basis sets, right? We have 3 linearly independent vectors for both C and B. That makes me extremely happy. So if I wanted to, only thing I have to do is create a augmented matrix. I want to go from C to B, right? C to B. That means that B is going to be on the right hand side. So I have 0, 2, 1, 2, negative 2, 1, 0, 1, 1, 1. And I should actually use a different color. I usually use a different color when I do the dots, don't I? Forgot all about that. It's been a while. Okay. And then on the, so C is going to be on the right side. 1, 2, 4, negative 1, 2, 0, 2, 4, 0. Okay. Do reduced row echelon form on it. Reduced row echelon form. And this is what I get when I do that. 1, 0, 0, 0, 1, 0, 0, 0, 1 on the left side. On the right side, I get, what do I get? Negative 7, 3, 10, 5, negative 1, negative 6, 11, negative 3, and negative 10. This is not my answer, right? This is not my final answer. This is not a transition matrix. This is an augmented matrix. My transition matrix from C to B is going to be that right-hand side. So I have negative 7, 3, 10, 5, negative 1, negative 6, 11, negative 3, and negative 10. Okay. And this is my answer. All right? All right. So that is change of basis, right? And like I said, you can extend this idea to functions. You can extend this into other polynomials. You can extend this idea to complex numbers. All types of mathematical objects can be, you can do a change of basis for, right? All types of mathematical objects. All right, so I will stop here, but we just did the simplest one. So I'll stop here for the day, and I'll see you guys next time.